let's say we have water. Water is flowing out at 10 feet cubed per minute. The water is flowing into a conical reservoir. This conical reservoir, point down, has height 10 and radius 4. So what's going to happen? Well, like all related rate problems, we have some action. Water is flowing into the reservoir. The water level is rising, up, up, up. So what's changing? Certainly the volume of water in the cone, also the height of the water here. And we'll call this distance h. And then this little distance here, r. So the question is going to be, find how fast the water level is rising, also known as dH dt, when h equals 5. In all of these related rate problems, there's an action and a freeze point. You'll always be given a situation and you'll be told when to freeze the action. In this case, we want the action to freeze when the height has gotten to 5. And the question then is, well, at that point, what is the instantaneous rate of change of the height? Well, you know what those words mean, don't you? dH dt. I think we have enough information to solve this problem. Let's try it. Step 1, do we understand the problem? I think we do. Water's flowing into a cone. It's filling up the cone. We are going to freeze when h equals 5. How about an equation? We've drawn the picture, we've labeled it. Volume of a cone. Boy, freshman geometry was a long time ago. I don't know about you, but I spent most of my time looking at the girl in front of me. But I do remember something about the volume of a cone. That's right, 1/3 pi r squared h. Now, I'm going to differentiate this, but as you can probably guess, if you look at that equation, I'm going to have some dr dt's, some dH dt's, and some dV dt's. What am I going to do? Well, fortunately, we have a solution to that problem. I don't want to deal with dr dt. And one of those properties, again, that I may have missed in freshman geometry was that the r over h ratio in a cone is always the same. Watch this. I know that r over h equals 4 over 10, or 2 over 5. So what we can do is we can get rid of all of the r terms. Do I want to deal with r? No. I only want to deal with what I'm given, 10 feet cubed per minute. Oh, that sounds like a slope or a rate of change, doesn't it? You bet it does. That's also known as dV dt. So I'm given dV dt, I'm given an r over h ratio, and I want to find dH dt when h equals 5. Let's make a substitution. I know that r equals 2/5 h. So now I can say v equals 1/3 pi 2/5 h squared h. Now again, I'm very excited and very pleased with myself. But before I make the substitution, what do I need to do? That's right. differentiate. You did a great job to get to this point, but take your time and finish the job. Before I differentiate, I'm going to make a little arithmetic maneuver to make my life a little simpler. 4 over 25 times 3, get my constant out here, and there's my variable, pi over 75 h cubed. 4 pi over 75 h cubed. Okay, let's continue on now. Differentiate dv dt, oh, with respect to t. Always with respect to t. 12 pi over 75 times h squared, that's right, dh dt. This is just like, and in fact, it is another implicit differentiation problem. This time, as all of these related rate problems, I'm differentiating with respect to t. Now, differentiate, then substitute. Let's take our values, plug them in, and get our answer. dv dt, given 10. Now I could be a good physics student and include my units and see that the units come out exactly the way I want. 12 pi over 75. H, of course, when h equals 5. 25 feet squared dh dt. And sure enough, all of you physics students know feet cubed per minute divided by feet squared, feet per minute. dh dt, change in height per time, that's right, feet per minute. So I can always use my units to help me check. At this point, I'm just going to plug in and get my answer. I can put these numbers in the calculator, evaluate them, 25 and 75, reduce 12 pi over 3, 4 pi, and so that's going to work out very, very nice. My answer is approximately 0.8. Now, will this be a positive 0.8 or a negative? Well, the height is rising, so it should be positive. And that's how this all works. We're very nice, we're very pleased. It comes out exactly the way we want it to. Approximately feet per minute. And if we were to go back and look at our steps from the previous lesson, we would see that we understand the situation, that we drew a picture, we came up with an equation, made a little substitution to get a better equation, and then, because we are aware of preventing premature evaluation, we differentiated, then substitute. And that, my friends, is your next lesson in related rate problems. You are now ready to tackle anything that your introductory calculus book and its authors can throw at you. Have a great night, good luck on those related rate problems, and always remember, differentiate, then substitute. Thank you.